Hello everyone. In this video, we are going to look at modeling fluid systems that have a non-compressible fluid. And the goal is to create basically something like a transfer function or look at the behavior of the system, but specifically from the standpoint of the S domain and transfer functions. And the goal is to create those so we can use them in controls of the systems. The material here is taken from Ogata, Modern Control Engineering, the amazing book that I have in lots of my videos. And the reason I'm doing this video and my next one, which is on thermal systems, that in my controls playlist, I have a video on modeling mechanical systems and one for electrical systems. And so if you looked at the book Ogata, it also talked about modeling fluid systems and thermal systems, and also in electrical systems, it also has modeling of operational amplifiers or op amps, which I have in one of my videos as well here. So if you want to be able to control a system, the first thing is you have to model the system behavior. And in classic control, you need to get a transfer function or a state space model for that. Then you can design a controller. So here we focus on fluids that are non-compressible, like water, regular oil, and so on. And so similar to what we had for a mechanical or electrical system, we want to define resistance in a fluid system, and we want to define capacitance for a fluid system, right? And we just going to mention inductance as well. So as I said in my video on electrical systems, basic electrical systems, you can say that mechanical systems, electricals, and fluid systems, they are very similar in to each other if you consider a specific basically cause and effect. For instance, if you look at the translational mechanical system, the cause of the motion is force, and the result of that is a linear velocity, right, or change in position. In a rotary system, similar, a torque is the cause of the motion, and angular velocity is, or rotational velocity is, the effect. In electrical system, the source of motion for electrons is a voltage difference, and the result is an electric current or motion of the electrons. Now, in a fluid system, the reason for motion is a pressure difference that you have in between 2 points, and the result of that is a fluid flow or flow rate, like Q, right? So this one is what we show in this note with small q that has units of like meters cubes per second. And then, as you'll see, the resistive elements are the ones that are wasting mechanical energy of the system. So for a translational system, that is going to be a translational damper. For a rotational system, it's going to be a rotational damper. For an electrical system, it's a resistor. Now for fluid system, it's going to be a valve. And I have to add one thing here. It could also be a pipe. So a pipe could also have resistance, which we're going to see. Then we have the ones that are storing energy, capacitative. So an electrical system is a capacitor that stores energy. In a translational system, it's the translational spring, and in a rotational system, it's a rotational or torsional spring. In a fluid system, it's a tank. That's where you store the fluid. And of course, inductance and inertia for a mechanical system, that's mass. This is resistance to change the velocity. In rotary systems, that is the mass moment of inertia. In an electrical system, that's the inductor, right, where it doesn't like to change, it doesn't like you to change the current. And in a fluid system, it's a pipe where it does resist you changing the flow rate by creating an opposite, basically pressure difference, okay? And here you can define inductance for a pipe. So the goal is basically to look at this. We want to look at this bottom part here. And for that, first we start with resistance. And we first define the resistance for a valve and in general, and then I show you how to go about a pipe. What is the resistance in a pipe? So for a valve, the resistance is defined as the R is defined as the change in the level difference divided by the change in flow rate. Okay, if you want to correctly show it, this is the formula for it: dH over dQ, where H is the head or level difference and Q is the flow rate. So dH over dQ is R. So this is the correct formula, the best formula that we have for resistance. Now you might say, what is this? This is when it's constant. This is when H versus Q is just a constant, which we're going to see. But in general, the actual formula for R is what you can see here, dH over dQ. Now, what is H? So here we assume that we have a tank, and this tank has a pipe that is, we don't consider this portion of the pipe, like we don't model this, we just model the resistance as just the valve. And we say this valve is going to resist the flow rate that is going through it, right? So if in the steady state situation, the height of this tank is H bar and the flow rate out of the valve is Q bar, then if the height in this tank, if the height of the fluid in this tank is a little bit disturbed, a little bit changed like H, and the flow rate is a little bit changed Q naught, then we can say that H over Q naught is going to be the resistance. So you see, this formula is the same as this one, because in this case, that H here is the change in the level, and that Q naught is the change in the flow rate. Okay, yes, so they are basically very similar, right? So you see that although here you don't have a D, because inside that H and inside that Q naught there is a delta or there is a D. There are changes. Now, in general, the question is, this H is what kind of function of Q? The head and the Q, what relation exists between them? And the thing is, well, if you look at this head and this flow rate Q, the function is not always a line. It could be a general, any arbitrary curve, right? Depending on the structure of this valve and the tank and everything. But so if there is a laminar flow rate where the Reynolds number is less than 2300, we can see that the H is basically H versus Q. The time derivative of that is simply going to be H over Q, basically. So if you look at it in that region, you can approximate it by a line and say that slope of it is a constant slope. But if the flow is turbulent, then R, which is dH over Q, if you want, you can show that it's going to be 2H over Q at any point. At any point H and Q, it's going to be 2H over Q, and that is not going to be constant. Okay, so resistance, when the flow comes out here, if the flow is laminar, which means smaller speeds, then we can say that this resistance is almost constant, while this flow rate, if it's bigger and the flow is faster, so you go to bigger Reynolds number and it becomes turbulent, then the resistance of this valve is not going to be constant. It's going to be variable. So it all depends on this H and Q, what relation exists between them, what is going to be this curve, right? Because many people will go and write the Bernoulli equation between, let's say, a point here and a point there, and they can see that, for instance, Q is proportional to square root of H, or H is proportional to Q squared, which you're going to see basically this parabola like that, yes? And in that case, of course, clearly the slope of this curve at any point dH over dQ is not going to be constant. The slope is constantly changing, right? And this Bernoulli equation, of course, when we write it and we get this formula here, we have some assumptions that we consider. So if those assumptions are valid, yes, we're going to get a curve like this and we can define the resistance. Now, in general, this resistance, whether constant or not, let's say even constant, this resistance depends on what? What parameters in this valve determine the resistance? Well, that's the shape of the valve, right? You know, there are all sorts of different valves that we have, from gate valve, globe valve, butterfly valve, needle valve. There are all sorts of valves. So this R is determined by the valve geometry and type. And the other thing is how much the valve is open. Is the valve open all the way, or it's just partially open or something? So in general, this resistance of the valve depends on a bunch of parameters, and it's not like a simple clean function that we can provide. Yes, there are some formulas that there is this K parameter for a valve, right? Which we call this the valve loss coefficient, right? And again, this loss coefficient depends on these parameters, so it entails those parameters. And then in that case, H and Q can be related to each other through this case. So H is equal to some parameter here, right? And if you wanted, this is like 2GA squared. Okay, so you see H is proportional to Q squared, and all the geometry and opening is concentrated into this experimental parameter, which we call valve loss coefficient. And so from here, if you take a derivative of H with respect to Q, you clearly can see that that your R, which is dH over Q, is going to be depending on the Q, and it is not going to be constant. Okay, so this is the definition of resistance: the change in the level behind the valve, the level of the fluid, over the change in the flow rate, dH over dQ. That's the definition of it. And as I said, this R is typically not known, and you have to determine that experimentally because it depends on lots of different things. So when you buy a valve, depending on the valve shape, geometry, and so on, you might get this K graph, a graph for K or values for K. So this is the resistance for a valve. Now, what about the pipe? We know that when the fluid passes through a pipe, always the pressure of the fluid drops. Why? Because, of course, your pipe interior, the inner diameter of the pipe, regardless of how smooth it looks like, if you look inside of this inner diameter, there is a bunch of basically surface roughness, right? So when fluid passes through that, clearly there will be some friction here, and you're going to lose some energy, which you can define it as a head drop or a pressure drop. So the question is, how much is the head drop when you go through a pipe? So one simple formula that you can find in the literature is called the Darcy-Weisbach equation, right? Where it says the head drop when you go through, the fluid goes through a pipe, is equal to FL over D V squared over 2G, where V is the speed of the fluid going through the pipe, the average speed, G is the G of gravity, L is the length of the pipe, D is the diameter of the pipe, and this F here is a number we call the Darcy friction factor. So of course, the rougher this inner surface is, the bigger that F is gonna be. And that F has to be determined experimentally again. Okay? So that F has to be determined experimentally. And similar to basically the resistance of in electric circuits, if you remember, in electric circuits, when current goes through a piece of basically conductor, the resistance of this conductor equals the special resistivity times L over A, correct? Where A was the cross section and L is the distance. And as you know, A is proportional to D squared, right? Now here is just proportional to D. So you see that the bigger the pipe is, of course, the smaller the bigger the head loss is, and the bigger the diameter of the pipe, the smaller the head loss is. And of course, the rougher the surface, the bigger the head loss, the bigger the velocity, the bigger the head loss with a factor 2. So this is the Darcy-Weisbach equation. Now, if you want to find a resistance out of this formula, first replace this V with flow rate Q. We know that V equals Q over A, and this A is pi D squared over 4. So if you replace it, V is 4 over Q over pi D squared. Plug it up here. Your H is going to be written in terms of Q like this. So head loss versus the flow rate can be written like that. Now R is dH over dQ. Take a derivative, and you see that the resistance for a pipe can be defined by 16 FL over pi squared GD to the 5Q. Clearly, first of all, you see it's not constant. It does depend on the flow rate. The bigger the flow rate, the bigger the resistance. You see it depends on this friction coefficient, it depends on this L, and it depends on the diameter. Okay, so here is a resistance that you can define for a pipe, and you can also define a general resistance for a valve, which, as I said, if you want, you can define it from here. So if I say, for instance, from here, if I want to define a resistance, clearly you can see that the resistance is going to be, let me come up here and write it for you. It is going to be K over G A squared times Q, right? Again, it's not constant, and it depends on the Q, it depends on A, and it depends on this valve loss coefficient. So these are the resistance for a pipe and a valve, okay? Now, what about capacitance? Capacitance, which is for storage, we define it, of course, for a tank where the fluid is stored. And capacitance is defined as the change in the liquid stored, the change in the volume of the liquid stored, divided by the change in the level of the liquid. Okay, so this H, which is the head or the level of the liquid, the change in that, and the change in the overall volume stored in the tank, those are the denominator and numerator for C. If you want to mathematically write it, it is equal to Q. Okay, you can write it in terms of their time derivative. Instead of these, you can divide them by time. And now the change in the head will be dH over dt, and the change in the volume is going to be the flow rate. So if you want a good formula for C, the formula is this one. C equals flow rate. This is the net flow rate, of course. This is the net flow rate, because a tank can have fluid inside of it and the fluid outside of it. So this is the Q net in the tank divided by the change in the height of the fluid. Okay, that's capacitance. Now, to show you that here, let's look at this example. So here we have one tank, and then we have one valve, outlet valve, and then we have one inlet valve. The inlet valve change in the flow rate is Qi, the outlet valve is Qo, and the height of the fluid in this tank with capacitance C is H. The resistance of the valve is R, and we do not model any pipe here. So we neglect the resistance of these short pipes because let's say the L for them is small. So we want a transfer function in this case. What transfer function? So in this case, this Qi is the input of the system, and the output of the system that we want to control is the height in the tank. So we want the transfer function of output over input, the Laplace of output over input, which is the transfer function of the system. How do we find it? Well, let's go and look at the definitions. So R, based on the definition for the valve, is the change in the height over the change in the flow rate. Now, in this case, what's the change in the height? Well, the change in the height is simply this H, because this H bar and Q bars, these are the steady state values. So the change in the height is H, and the change in the flow rate coming out of the valve is Q naught. So H over Q naught is going to be R of the valve, okay? What about C? Remember, C is the Q net. In this case, Qi is going in, so it's positive. Qo is going out, so it's negative. So the total flow rate net is Qi minus Qo. And the rate of change of height is dH over dt. Yes? So if I cross multiply this, you get RC dH over dt equals Qi. Now you might say, where did you get this one from? Well, if I cross multiply this first, you get Qi minus Qo equals C dH over dt. Yep. From here, you can see that Q naught equals H over R. So I can plug it up here, right? Let me bring these two in one place. It is going to be Qi minus H over R equals C dH over dt. Now I multiply both sides by R, so this guy becomes R C dH over dt. This becomes just H, and this becomes RQi. And then I take this H to the other side. So it becomes RCdH over dt plus H equals RQi, which is this equation here. There we go. Now this equation is only between input and output, Qi and H. So all you need to do is to take a Laplace transform. All you need is apply a Laplace transform to this. So that becomes R times C times S, H of S, and then plus H of S equals R times Qi of S. So here you can factor the H out, so it's going to be 1 plus RCS, divide, and this is going to be your transfer function. So clearly in this case, the height as a function of the inlet flow rate is a first order system. It is what? It is a first order system like an RC circuit. For instance, if I have a fixed Qi, so let's say Qi equals some constant, and this is H versus time, and let's say initial H is 0, so the tank is initially empty. You start with a constant, so you open this valve and you let in a constant flow rate. We want to know how H changes versus time. Well, all I need to look is either this equation or this one of these two, right? So what happens? This is a first order system. The time constant of the system is RC. So it is going to go exponential. And the final value, as you can see, when this dH over dt is 0, the final value should be equal to RQi. So the final value of it is R times Qi and you start from 0, and then exponentially you go up to this number. So the tank will get filled up to the level RQI, and that is where the height does not change anymore. How much time does it take? Well, in terms of a control system, the time here is about 5 times time constant of the system, tau. What is tau? In this case, your tau is R times C. So it is going to be basically 5 times R times C. The resistance of the valve times the capacitance of the tank. Okay? That's it. That's all you have is that's basically the time it takes the tank to be filled. And after that, it's not going to go any further up. You might say, why not? I'm filling it in. Why doesn't it go up? Because on this other side, you are what? You have some QI. So the bigger the H becomes, the QO. The bigger your height goes, the bigger the output flow rate is. And your net flow rate is QI minus O. So yes, this QI stays constant, but after some time, QO is big enough to not let the height change. So basically those two cancel each other. QO reaches the level QI, and that is where your H is not going to change anymore. Now, theoretically, it takes forever, infinity, but in practice, it's almost about 5 time constant, where you get to 99.5 or 9% of the steady state height. One last thing before I go to inductance is if this tank has a constant cross section, okay? So if the cross section of this tank is constant A, then C is equal to A basically, because this is like the change in volume, delta V, divided by the change in the A delta H, and as you know, V equals A times H, right? So from here, delta V equals A delta H, and so that is going to be equal to A. So you see that the capacitance for a tank, if the cross-section is constant, is equal to its cross-section. Okay, so in terms of the geometry of the tank, you can see, because what I'm trying to tell you is basically, if there is anything we know about the geometry of these elements that relates to the resistance or capacitance. Now, for a pipe, if the pipe has cross-section A and length L, we can also define inductance. Inductance is what? Inductance is the change in the pressure across the pipe divided by the change in flow rate, and that is going to be L over A. Okay, and if you want, we can prove that, but here my goal is not to go through that. So the inductance for a section of a pipe is L over A. So you see clearly, bigger the L, smaller the A, you have a bigger inductance, and inductance is similar to inertia. That means it does not like you to change the flow rate. Okay, a pipe does not want you to change the flow rate in it. If you do, it is going to give you a resistance. It is going to try to give you a pressure drop. Okay, now to make this complete, remember in electric circuits, we had, when we wanted to model the electric circuits, basically we had the capacitor element, we had the inductor element, and we had the resistor element. Now here in the fluid system, we have similar things. So now we have the valve and pipe, as I said, for the resistance. For the capacitance, we have the tank. And for inductance, we have the portion of the pipe, right? That we talked about. For the voltage difference, here we have pressure difference. And for electric current, we have flow rate. Good. Now remember, in electric circuits, we had two important laws which were the essence of electric circuit analysis. One was the Kirchhoff voltage law, which said if you have, for instance, a resistor here, a capacitor there, or anything else, and this is some voltage, correct? It says that if you go around any loop, sum of the electric voltages across the loop equals 0. Yes? The other thing was, if you have any, that was called the KVL, Kirchhoff's voltage law. The other one was, if you have any junction or node, sum of the current going in equals sum of the current going out. So if this one is I1 going in and these two guys are I2 and I3 going out, then I1 should be equal to I2 plus I3. This one we call the node law, or the Kirchhoff's current, basically, law. Now we have something similar to this for a fluid system. In a fluid system, if we have a T, right? So if we have a T in a fluid system, and this guy that is coming in is, for instance, Q1, flow rate is going in, and then at this T, it goes to Q2 and Q3, then the same thing, Q1 equals Q2 plus Q3, because here the fluid cannot disappear or be generated. So some of those two flow rates should be equal to Q1, and that is basically what you can see here, right? If you consider some of them positive, some of them negative, you can say some of the Q's equal 0 or some equal the other one. And then instead of some of the electric voltage across a loop, around the loop equals 0, here you can say some of the pressure drop in any loop equals to the 0. Okay, and this one is basically similar to the Kirchhoff voltage law. Now, let me explain this. You might say, so far you all the time talked about head when you talked about the resistance or capacitance. If you go back, you were talking about head here and head here. How come instead of head now, all of a sudden you talk about the pressure? The thing is, the pressure in the fluid is proportional to the head. Okay, so instead of saying here basically sum of the heads equal 0, we say sum of the pressure differences is equal to 0 around when you go around the loop. Okay, because pressure is proportional to the head here. So that is something important that I wanted to emphasize for you. So these are similar to Kirchhoff voltage and current law. Now here, let's look at another example. So here now you have 2 tanks and 3 valves. Valve, this one brings in the inlet flow Q. So that's your input of the system. And the change in the height of this first tank is called H1. The capacitance of that is C1. Remember, C is kind of like cross-section of it. The first valve, which sends the fluid to the second valve, the flow rate of it, the change in the flow rate of it is Q1. The resistance of it is R1. The second tank has the change in the height of H2, a capacitance C2, and then finally there is an exit valve which has the flow rate change of Q2 and the resistance of R2. So what is it that you want? You want to find this, if this is what I want to control the flow rate out of the last tank, so that is my output of the system, and the input is the first Q, so I want Q2 of S over Q of S, okay, output over input. How can you find that for me in here where I have 3 valves and 2 tanks, okay? And again, I do not model any pipe. If you wanted to model a pipe, let's say here, you had to model one resistance here, maybe one resistance there, one here, one there, okay? So if you wanted to model those resistances based on this formula that I showed you, you could have done that as well. But here we assume that either those pipes are very smooth or their length is small, so the resistance is negligible compared to the valves. So here we are just neglecting them. Otherwise, you would have 1 R here and then 1 R here, and then you can have all those 3 R's in series and these R's in series. So the equivalent here is going to be some of them. The equivalent here is going to be some of them, right? So, and then you can write it. But here we just neglect those. So what do we have now? Well, we go based on the definition. What's the definition of R1? Based on what we'll know, R1 is the change. Let's go back and look at the definition of R1. R1, the definition of it is what? It says it's basically the change in the head divided by the change in the flow rate. Okay, that's the definition of it. Now, in this case, R1 is situated between two heights, H1 and H2. So the change in the height is the change in the height of this one minus that is the net change. So in this case is H1 minus H2, and the flow rate through it is Q1. So it's this guy. The change in the flow rate of it, not the flow rate through it. The change in the flow rate of it is Q1. So that is definition of R1. Now for R2, that's not the case. R2, here on one side of it, the height is H2. On this side, there is no tank. So it's simply H2 minus 0. And then the change in the flow rate of it is Q2. So you can write it divided by Q2. Okay? So in this equation, in this top one, if you swap Q1 and R1, you get this equation. And in this bottom one, if you swap R2 and Q2, then you get this equation. Okay, so these are the first and the third equation that I have here. What about equations 2 and 4? Where do I get these ones? Well, for 2 and 4, I need to look back at the definition of capacitor, or capacitance, sorry. Capacitance is Q over the change in the H, okay? Q over dH over dt. So what's the C1? What's the definition of C1? C1 is equal to, remember, again, Q over dH over dt. So in this case, for this tank, what is the Q net? Q net, Q is coming in, Q1 is going out. So it's going to be Q minus Q1, that's the net Q, over the D of which H? The change in it is H1, so it's D of H1 over dt. Remember, this H bar is a constant, so if you take time derivative of that, it's just 0. Now in this case, if I cross multiply the C1 and dH over dt, then I'm going to get this equation here. And then, of course, the definition of C2 is what? C2 is the net Q. What is the net Q? Here, Q1 goes into the tank, Q2 goes out. So it's Q1 minus Q2 divided by d over dt of its change in height, which is H2. Again, if I cross multiply these two, then I should get equation number 4. There we go. So based on the definitions of resistance and capacitance, now I could write for you equations 1, 2, 3, 4. Now, are these equations enough to give me my transfer functions? So the thing that I always ask my students to do in the class is, first, make sure that you mark down the knowns and the unknowns. Make sure you have enough equations for your unknowns. If that's the case, then guess what? Yes, now you can solve for it. So the question is, in this system, how many knowns and unknowns do I have? So for the moment, let's say the input is given to us. We want to find the output, right? That ratio, when we talk about the ratio, this is another way to talk about it is, hey, I know the input, give me the output, right? So Q2 is output, Q is input, and is given. So one of your unknowns is Q2, fine, Q2 is unknown. What about this intermediate fluid? Do you know it anywhere? No. So that's another unknown that you have here. And you also have here and here and here. So 2 unknowns. What about the changes in the heights, these H1 and H2? Do you know them? No, we don't. Right? We don't know them here. So how many unknowns do you have? 4. The unknowns are H1, Q1, H2, and Q2. These 4 are unknowns. The given one is the Q itself. So I have 4 unknowns, and of course what? How many equations? 4. So 4 equations, 4 unknowns means you're good. You have enough equations here to be able to solve for Q2. Now, how do we do that? Well, let me show you. So here I need to do a little bit clean up so you can see how I do the elimination here. Or if you don't want to do the elimination, what you can do is to go with write them as a linear system of equations, and then 4 by 4, and then solve for all of them. The one that you care about is Q2. You find it, it's going to be a function of Q, then you divide that and you're good to go. But let me show you, if you want to go elimination, how would you do elimination in this case? So remember, the goal is Q2. That's what we care about. So we have to get rid of Q1 and H1 and H2. How do we get rid of Q1? Directly using equation 1. Wherever I see Q1, I replace it by H1 minus H2 over R. So that is going to sit here, and it is going to sit right there. Okay, so that is going to get rid of Q1. So now your equations are going to be basically, and if you cross multiply them, you get H1 minus H2 over R, right? And Q minus that. This is equal to C1 d of H1 over dt. That's equation number 2, the new version of it. Now equation number 3 is not going to be affected, so we can leave it as is. And then we are going to go with the last equation. So let me write the equation number 3, which is whatever it was. So it's just H2 over R2 is Q2. And then the last equation is going to be that same H1 minus H2 over R. And by the way, we have to pay attention to which R we are talking about. Okay, so this is R1. Right? So that is Q1, and then minus Q2 equals C2 d of H2 over dt. There we go. So Q1 is taken. Now you can eliminate H1 and H2 if you want. Now, before I do that, the best way to do it is to use a Laplace transform. Okay, so if you do Laplace transform, then these derivatives will be converted to some s times something, so they become algebraic equations. So your ODEs become algebraic equations. So instead of going all the way to here, I apply a Laplace transform somewhere also in the middle. If I do that, now this is going to be a little bit more interesting. Why? Because this guy is going to be Q of S. This is going to be H1. This is going to be H2. And then instead of this dH1 over dt, it's simply going to be S times H1. Okay, you see now you have an algebraic equation. Here, of course, this one and this one, you can just replace with their capital letters, which stands for the Laplace domain or S domain. And then we have these guys. So that's H1 and H2. This is going to be Q2. And this is going to be S times that. There we go. Okay, and now you need to get rid of H1 and H2. So there are lots of different ways to do it. For instance, from this one here, you can solve for H2, right? H2 equals R2Q2. So now this can go wherever H2 is. So that can go here, it can go there, and it can go here. Okay, that will get rid of H2. So if I write the first and the last equation, this is going to be, especially if I multiply both sides of it by R1, it's going to be R1Q minus H1 plus H2, which is this one, equals R1C1 S times H1. That's your first equation. And the last equation, again, if I multiply by R1, it's going to be H1 minus R2Q2. And then minus R1Q2. This is equal to R1C2 S times R1C2 S times R2Q2. So like this. There we go. So now you see here, I basically eliminated H2. Now all I need is to eliminate H1. And I can do that as well here by taking this H1 to this side. If you factor it out, then the right-hand side is going to be H1 times 1 plus R1C1S. That is going to be equal to R1Q minus or plus R2Q2, right? So let's solve for H1. H1 is going to be R1Q plus R2Q2 divided by all of that. And now this is all you need to plug in right down here. And if you do that, now your final equation is going to be only in terms of Q2, which, by the way, you can take these negative terms to this side, and in terms of Q. So now you will have one equation only in terms of Q and Q2. And from there, if you solve for Q2 and divide by Q, this is going to be your final transfer function, which clearly it is going to be a second order system. And these are the coefficients of that second order system. Okay? So in this case, for instance, if Q is a fixed input, a constant input like a step function, you can see that the flow rate out of the last tank, Q2, could either be basically an exponential behavior or an oscillating exponential behavior, depending on the roots of this characteristic equation. Okay, and you can basically look at the behavior of the second order system. So any tank and any resistor that you will add, that's a first order system based on what we learned up here. Sorry. Seems like it gone a little bit crazy here. So each tank and each resistor after that is a first order system. So if you have two of that back to back, that's two first order systems in series. So you get the second order systems as you can, a second order system as you can see here. So hopefully this introduction was useful to you. You can see the similarities between a compressible fluid system and a mechanical or electrical system, and the definitions for resistance, capacitance, and inductance, and how to find transfer functions for the sake of controls of these systems. Thank you so much, and I'll see you in the next video.